So we're back at the comparison stuff. So Anaconda, let me see, where did I leave? So if I go to my workspace, so the Grover Nisk, exactly, and we've got here. Basically, I'll should just probably Jupyter Notebook, start the whole thing. Am I connected? Jupyter Notebook. So give me a second. Cool. So this is opening up. Okay. Now where were you? Where was I? So I was basically testing the functions, right? So I was testing step by step. Maybe you should clean up some of these things, to be honest. Let me open these notebooks and see which ones can be deleted. So, or at least moved into some kind of archive or something. So new folder. New folder. How can I name that? How can I rename that? Rename. So I'll call it. I'm gonna move stuff in here. What's my battery? Okay, cool. So air introduction. Okay, so that was the stuff for the air correction. Definitely to move. This air mitigation as well. So I want to focus on the actual comparison now. So Grover Nisk, I think this is the so this is my actual stuff. Okay, this is my actual work cleaned up. So K13, K14. That was 20 February. This is I don't really know which one was which one is really the latest. I'll just keep those two. So I'll actually move these as well. And okay, so this is basically, I'll rename these. No, this is paper. So I'll add this in here, so I know it's from the paper. These TOEFL test. Okay, this is why I was doing the comparison of the TOEFL last time, and ended up with, okay, that's cool. Meaning that both implementations work, which is good. Which is good. And all this bunch of untitled stuff, I think this was early tests. Oops, I think I just showed my key. Okay, so these, what is these? This is another stuff with the TOEFL, right? Yeah. And this is also the paper one. Okay. So good. Now that we have that clear, so I'm gonna take all these untitled and I'm gonna view edit. Come on, I cannot move them. I cannot duplicate, shut down, view, edit. I cannot move them here. Okay, that's weird. I thought I could move stuff. What if I duplicate? No, but that's going to duplicate in the same folder. Okay, whatever. So it's for nothing. Now, anyway, my goal with this video is to keep going with the comparison. I think the next step here would be that I compare the because if I take a look at, so I compared the R TOEFL M, the TOEFL IX, the Toffoli gate with one swap has been compared as well. Device topology optimal multi-control X. So here's where we've got the basically the uncomputation. That's the stuff that I don't have. And then we're done, right? Because subdivided phase Oracle global algorithm for Max-Cut problems. So what is this? Initialization, the subdivided Oracle diffusion. Yeah, and then define the circuit. So the code seems really to be define number of data in Grover's algorithm. Shots. 4 types of quantum circuit, define the transpiler. So here they do take a look at whatever. Toffoli decompose, preserves Toffoli decompose, optimize 1Q gates, unroller. I really don't know what this is, a transpiler. That's something that we could definitely take a look at. Compose each circuit. Circuit number 1, the approximate Grover circuit. So here they basically go and make all that stuff. And then there's the transpile circuit. And then there's the circuit number 2, so that's another circuit. Circuit number 3. Transpiled circuit number 4. So they generate all the possible circuits. Chasm simulator, and then they go ahead and do the simulations, which the simulations match. So from that perspective, I think it just works. It's just the real device didn't seem to work, but I now understand that this is extremely machine dependent. But on their case, they were getting nice numbers, I think. Plot the results. Post data processing. This bubbling and they were getting, I mean, again, this is literally not working. Read out errors. Plot results. Yeah. And if I exactly say here with the 4 qubits, it didn't work either. But then they did this with another machine, right? That was this one in here. And that is so they're the same 4 circuits. Four circuits. Should probably compare this one then, because here with Valencia works a little bit better, but it's also not extremely. It's also not extremely good, because this should be the. It's also not extremely good, to be honest, but it's better. Yeah. Question is the same code or is it the same code? Initialize. So this is Rother in terms of the RTOF gates, Toffoli swap, finding the 4 circuits. So I'm interested. It's interesting how they actually do the initialization. Maybe I should take a look at this as well. Okay, it's part of the fusion operator. Part 3. What? Grover circuit. So okay, so they literally number 1, number 2, number 3, number 4, the Grover circuit. Wait a second, do they uncompute in here? RTOF M, TOEFL swap, RTOF M. They do uncompute. They do uncompute. Apply transpile. So I will take a look at two things. I'll take a look at I want to take a look at this initial preparation, where this is. Where was this? 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 I saw this here in the circuit. Oh, here they don't go through. Okay, so here, if I go up to the... So I want to take a look at this portion in here. So this part in here. Another, yeah, because here they use RZ gates. Pi4, RZ gates. Maybe it's time to clarify this. Maybe it's time to clarify this. Try to clarify this RZ, and then the uncomputation. If I can touch these two topics, I'll be super happy. Because I think from that perspective, the rest is just it seems it's working. So it seems really the code portions are the same. The code behaves the same. Those are just the 2 points where I'm not completely sure, and then we can dive into the other topics like quantum volume and all this other kind of stuff. That is definitely interesting diving into as well. Quantum volume, the whole thing here with the performance, how they measure all this kind of performances and all that stuff, which I think it's kind of, which could be crucial for debugging all these, all these different things at some point. At least the transition between the ideal world of the simulation and actual devices. But let's take a look at this. So first of all, let me open the... This has been a topic that's been bothering me for a long time. The difference. So, and it's just, I think it's just a matter of it's a rather a lack of a conceptual clarity than anything else. But it's just the fact that when you... So we talked about the RZ gates, right? And so I all the time think that, or all the time assume that what we're using is Z rotations and not the RZ gate, which is different. It's different in terms of how the phase is working here, because there's no global phase in here, right? And so if I rotate, let's say if I rotate a qubit, right? 1/4. So I get these in here, right? Yeah. If instead of that, I use an RZ and I rotate it pi divided by 4. It's for this case works. It's 22.5 degrees of phase plus 0.9 plus 0.38 I. 1/4. Okay, no, it's it's definitely different. So, but yeah, because pi 2, so, okay, because pi divided by 2, so this difference is by pi divided by 2, so here you specify the angle in radians, here you specify sort of the fraction that you're rotating, right? But, so this should be the same as pi divided by 2 should be our 1/4 rotation, yeah. The problem that I have here is that when we do this on the plus state, they behave differently, right? So a 1 divided by 4 rotation on this gives me a relative phase of 45 degrees, right? Whereas a pi divided by 2 rotation here, it really, the relative phase is 90 degrees. That's the problem, because it rotates both components. And so this is in Quirk, okay? Now, how does this translate with the quantum experience? I don't really know. Let's take a look at this. So IBM. Let's take a look at the composer. So I'm gonna call it RZ versus Z. I just logged in right now. So because really this is what's in here. So it's the difference in here is they are, so there's the Hadamard gates and then there's this pi divided by 4 RZ rotation. So let's say the following. We want just 1 qubit, just to make it simpler. And we want to have a Hadamard, so we're here like that. And now we apply an RZ, but I can't. Yeah, I can parameterize that. So an RZ of pi divided by 2. State vector. Pi divided by 4. Pi divided by. So we compare it to Quirk, right? Pi divided by 2. Let's do pi divided by 2. Okay, so it gives us this state like 0.7 plus 0 imaginary and then 0 plus 0.7 imaginary. And here we've got a state so here we've got a, it's different really. That sucks. Pi divided by 2, okay? Pi divided by 2. This is RZ pi divided by 2, so this is definitely a different state. It's plus 0.5 minus 0.5 imaginary, plus 0.5 plus 0.5 imaginary. Okay. But if I use these, so and I do a 1/4 rotation, then I get state, keep it 0. Component 1 component. What am I looking at here though? I think I want to So the amplitude for 0 and amplitude for 1. So the amplitude for 0 is 0.7 plus 0i, right? And here 0.7 plus 0i, that's correct. But then that is 0.5 plus 0.5i. And here we got totally something different. Pi divided by 2. And here we have a 1/4, which should be the same rotation. Again, if let me just, this is just so confusing. Pi divided by 2, where are we? Pi divided by 2 RZ. It's just different. Or is it that this is what's confusing me all the time. So what's the kind of correct way to implement that? Because this is an RZ pi divided by 4, which is translated. This transpiling happens like, yeah, basically. Because if I would use the U1 instead of the RZ, so remember this is 0.7, yeah. So if I would use the U1, right, and I would say pi divided by 2. Can I say can I do something like that? No, that's not the way this works. We're getting the same, literally, because it seems like in the IBM Q experience, the RZ is really that the RZ gate rotates around the Z by an angle and radians determined by a formula. Rotates around the Z by an amount determined by a formula. Because this seems it's adding, it keeps a constant relative phase of 90 degrees. No, that's not true either. Is it? So here the relative phase is, no, it goes, okay, the relative phase increases up to 180 degrees. But then this means that this state is equivalent to the state where this is 0 and this is 90, right? So this means that RZ pi divided by 2 is equivalent to the state that you can generate with a Z 1/4. Z 1/4, not 1/4, but 1/2. So that should be equivalent. Because the relative phase is what matters at the end of the day. 1/2, if it's divided by 2, right? So it's 90 degrees. If it's divided by 4, pi divided by 4, then you've got a relative phase of about 45 degrees, right? And that should be equivalent to to this state. Basically 1/4. Now, question is, the issue here is that while I must assume that's true, I have a hard time understanding why doesn't this matter, because then the effectively, if I now apply a Hadamard here, for example, we get the state, right? And if I just take this here, and now I apply an RZ gate that is a pi divided by 4. Yeah, so you're getting the same amplitudes, and the phases are just the phases are different, but the relative phases what matters. Okay, so this is all fine. This is all fine. So those are really equivalent. It's just that one rotates also the amplitudes of zeros, and the other one doesn't. But then, if I go back here, so then what do they do, right? So they do pi divided by 4 RZ rotations in here. And what do I do? What do I do? What do I do? What do I do? Hadamards? The oracle. Where's the oracle? Where's my oracle? Theta. Pi divided by 3. Oh yeah, because this is, okay, so I do pi divided by 4. U1 theta, which is pi divided by 4. But then we just said that pi divided by 4 should be the same as RZ. So U3 pi divided by 4 right? It's should be the same as a 0.7 real 0.7 and then 0.5 real, 0.5 imaginary. Pi divided by 4. 1. Let's see, no, RZ. Pi divided by 4 should give us the same. Yes. Okay, cool. So then we're cool. So this is not a. For some reason I prefer to use the U1 gates. It just, I don't know. It feels cleaner because the phase for the zero amplitude stays at 0. It's easy to take a look at interference patterns afterwards. I have the impression, so that should be fine. Okay, good. 1 point checked. And then I want to take a look at the uncomputation part. How would I approach that? So basically what they do, right, is in the paper, they uncompute the Toffoli gates in the multi-control Toffoli. And they do these where is it? And the CNX circuit. So they do RTOF M, then they do 4D in range, and then they just iterate over that and apply the RTOF M. Then they apply a Toffoli swap at the end, and then they apply another RTOF M here. Sorry, here. Backwards, and then one last part of him. So basically what they do is they go and they do the equivalent of, you know, it's like these, and then they go like these, right? And then they do like these, because the idea is that this qubit here is supposed to be an ancillary qubit. Let me make it easier to take a look at and to analyze. If I move this qubit, how can I do that? I think it was, no. How can I track this? To the top, maybe? Yeah, I don't know. Just take a look at this. So the idea is this is an ancillary qubit, and so these are our actual three inputs. So if we put these, and this is the target, right? So if you put this in superposition and just take a look at these, and we ignore the ancilla qubit, right? So our target qubit in here is the leftmost. So we can see that here all these are valid solutions because they don't have like all the possible combinations of zeros and ones. For the three rightmost qubits, they never have a 1 1 1, so it's all 0. And then these are non-valid solutions, and then this is a valid solution. So this is the uncompute. The uncompute works well. If I ignore this, does this change? It doesn't change. But pay attention that it says it's incoherent, entangled with other qubits, and the reason is it's. I think the reason here is that we have an uncompute. So if I would now do something with the ancilla qubit, what can I do? That's incoherent, so it's entangled. So you want to uncompute that to probably avoid undesired effects. If this is 1 1 1, like that's all fine, right? That's all fine. It's just the problem comes when you've got superpositions in here, because now you've basically entangled, like you've entangled here, you've created entanglement, right? And then here you've create more entanglement. So the problem is, if you don't uncompute, then you can't use that ancilla qubit anymore, because it's basically entangled. This means that the measurement and the state of this is going to really depend on the state of the other qubits you've entangled it with. So if let's say, how can I take a look at these? No. So if I were to, let's get rid of these for a second. If I negate that, so does this change? It does change my state, right? Because then because then I've got this in here, this in here. How could I see? How would I be able to see that? That this affects like the target qubit in here, which is basically oh yeah, because it's really the measurement. It's really the measurement. It's really at the measurement point where things get messy, right? Because we keep them entangled. And so in theory, right, if I say, for example, let's pause select and let's assume that this is gonna, let's pause select for 0, right? What does it do to our state? What, it doesn't seem to do anything bad. If I pause select for 1, if I pause select for 1, well, then it does seem to basically 1, 1, 0, 1, 1, 1. If I pause select for 1, it still leaves me with a probability. What if I take a look at these now? That collapses the state in something super weird, right? Is it? Because yeah, that's not what we want. We want these measurements to be independent. If I uncompute and then I pause select, that shouldn't happen, I think. Yeah, because it emits 100%. Because then if you pause select for 0, that still leaves you the state that you want to be in. But if I don't uncompute and I pause select for 0, then it doesn't. Then it leaves this in a state that's not the one that I want. Well, basically, it makes you see. Okay, so that's the problem. The problem is as soon as you measure these, then you're going to get into trouble because now your state is not a valid Toffoli state for a superposition input state because you don't have that solution that should be valid is not existing in your superposition anymore because you've pause selected for 0 here. So basically, basically that entanglement is hurting you because it means that you've pause selected in 0 for here 0. So it means this could have never been a 1-1 combination, and so that's why it leaves you with that state, and that's not what you want. Because I mean that's just dangerous. That's why you uncompute, and why when you uncompute you leave the superposition and its proper state. If I now uncompute, bam, we're all good. We are all good. So you got those two states back, which are the ones that you're losing before, and especially this one is the important one, right? So pause selection is important. As such the uncomputation is important as long as we kind of measure the qubit. So, and that's something that I was not doing in my circuit in here. I didn't do that. So, in order to do that, I would need to add that circuit one again. So, but again, as we are not measuring the ancilla qubit, which is Q4, right? Oh crap, we're measuring it. We're indeed measuring it, but we're measuring it at the very end. I mean, the simulation results seem to be good anyway because we're measuring at the very end. Yeah. So in this case, because of the nature of the machine, I think that's not a problem. I wouldn't definitely change anything here, but I can try. I mean, if I would, you know, I would. I think I would have to do these again, right? So if I would do these again, if I, let's say, run everything up to this point, let's see what we get. But that really should be it. Cool. Is it working or not? But I mean, after we're done with this, really, I think we're done with the analysis of the code. The code seems to be the same, and so it's not. This is not really overly complicated. They use a different approach to the amplitude amplification with the Z and the Hadamard layers instead of a Hadamard and a NOT layer. But those are equivalent. Yeah, so I think we're pretty much good to go. What's the... Okay, so now we've got these basically. So, move forward. Oh, it's Q1 the ancilla, is it? Yeah, sorry, it's Q1 the ancilla. Yeah, it's Q1 the ancilla, and we don't measure it. Ah, okay, so so we're good to go. But let's see what happens if I measure it. Okay, let's do the experiment. So let's basically do not do that. Let's try this. So let's not do these. And now let's simply measure 1 as well. So let's have 5 in here. But if I measure it, then it's going to be difficult to interpret the results, is it? Because it's a qubit that I... Well, to be honest, it's a qubit that should always be 1, should it? Huh. But let's say 5. So let's say that I measure 0, 2, 3, 4, 2. Okay, so what I will do is I'll measure it in the last qubit, so I can then ignore it easily. So I basically measure these in the 5th classical qubit. So I will do this. I'll draw this exactly. So this is measured in the last qubit. So we only care execute in simulator. Qt done, and then I think I just want to take a look at the simulation, okay? So I'm gonna basically need to do that. Let's wait also for the... Yeah, but I don't know if the real device is not right now being just to be... So I'll command that, and I'll basically remove this from here. Remove this from here. Look at the simulation results. If that executes, and see if that would be anyhow different if we measure that. But we should measure it first, maybe, to see the effects. Probably. So what I should probably do, out of curiosity, is circuit circuit rear, and then circuit measure 1 to 5. So where is this taking us now? Sorry, I should have done this way. Too much because I messed up with this. So I shouldn't execute it on Berlin, on this computer at all, on this machine at all. Can I just cancel this stuff? Stop, interrupt the kernel, interrupt the kernel. Okay, so can I now do this? I gotta start from scratch. So we got this. We're not uncomputing. What's going on now? Measure 1, 5. During handling the listing is out of range. Oh, sorry, 4. Now draw the circuit. Okay, so now we've measured these first, and now things should be messed up, I think. Let's see if things are messed up though. So we're measuring. And we only care about the 0 to 3 qubits in here. So simulate a job. This guy done. Simulate results. Plot. Yeah, okay, interesting. So what have we got in here? Yeah, but I mean, actually, it actually, it's not that weird really. Like you've got basically a symmetry in the results, but it seems to work anyway, right? I guess the problem is not just these. The problem is if I would like to now do something with after that measurement, if I'd like to do something with it, quantum wise, right? I guess that's the point. Is if I would like to do something with it farther in the circuit, if that would be part of a bigger circuit, that would just spoil it spoils my state, right? If I don't do this, if I don't compute. So now basically, I wouldn't be able to keep working on this, I guess. Or I'm not so sure how to read these, how to interpret these then. I mean, this seems to be more, this seems to be noisier because you've got here these things. This simulation seems to be noisier, but still the right solutions are there, right? Which is the last one. Interesting. So I'm not so happy with this. I'm not so happy with this. Because with path selection, it basically, I think it shouldn't work. Right? I mean, this one here is this. So if if this qubit is 0, I think that's the so that's going to be in the qubit 4. And qubit 4 is what? Is it this qubit? Yeah. Is this classical bit 4? I think so. Like if this is measured 0, you've got still that. Huh. You know, I basically wanted to do the I don't know why this works. I don't know why this seems to work though. It seems like it shouldn't work. Because let's assume that you're getting a 0, right? And then it means we're just half of the state. Half of this is what you should get. Hmm. That's not what I expected. So I probably need to dig a bit more into this, but and I measured the right thing, right? So I'm measuring. Oh, wait a second. I'm doing something wrong, maybe. I think I'm doing something wrong. Give me a second. No, that's correct. The Q1 doesn't have any Hadamard in here. Okay, fair enough. I thought I was putting a Hadamard. I was putting a Hadamard in here, which would be not the right thing to do. So to be honest, this feels like it shouldn't work, but I'm maybe missing. I'm missing something, as in like. Is it maybe the way I keep forgetting in what order these things are measured? What if I add like this 6 in here, and I put this into 5? So this should be basically there should be a one qubit that it's always 0, and then this one should be the one next to it. Just to make sure that I understand where this is placed, right? Yeah. This is so you see this is all. So this is all zeros, right? Here, this is all zeros, and then the next one is the ancilla qubit. If we measure the ancilla qubit to be 0, there are certain things that shouldn't happen, like especially the correct solution shouldn't be there. That's what's confusing me the most, because or is it? I'm not uncomputing, correct? I'm not uncomputing. So I do these and these, and if qubit 1 is 0, oh, so it's Q4 in here. Yeah, okay. Sorry, here's Q4, but it's Q1 in the bigger circuit. That's all fine. That's all fine.
that's the final circuit in here. I think this definitely shouldn't work. I don't know why it works. I have the impression this shouldn't work. So I probably need to think about this a bit more. Yeah. But okay. Cool. This shouldn't be the case, but maybe I'm missing something. But that's, in theory, that's what I would expect. I would expect that the whole thing doesn't work if you don't uncompute and you measure the ancilla, the ancillary qubit, because the ancillary qubit and you measure it to be 0. That's the point in here. For those cases where you measure it to be 0, then the whole thing shouldn't work. Nevertheless, we see in here that some seem to work. Where am I? Because you've got some with 0 here, and you still get the right solution in here, which you shouldn't if you set this to 0, because it means those are not possible solutions. You shouldn't be able to see those solutions. Definitely. That's something that I want to deep dive into. Cool, perfect. Enough for today, though.